Wasabi, you guys. Welcome to Integration Be Trading for Advanced. This is part 18.2. In this section, we're going to be applying Euler's reflection with some trickier integrals. Okay? So let's get started. Alright, so we have the integral from 0 to infinity, dx over x plus 1 times x to the power of 3/4. So here, what we can do is I'm going to go ahead and lift that x, this part here, and we're going to put it on top. So this would be negative 3/4, and then x plus 1. If you remember the beta function, in a way, right? So anything like this, where you have x plus 1, and there's no exponent here, then that's how you know we're going to be using Euler's reflection. Okay? This is based off, if you remember from the beta function video. I think that was part of the intermediate series, where we have x to the power. Well, let me write this. We had m plus 1. I'm sorry, no, this is m plus n, and this is m minus 1. And this was the beta function of m and n. Okay, if m plus n is equal to 1. Okay, then what this means is that m is equal to 1 minus n. And now this portion here, well, I mean, I think you get the idea of where this goes. I think this is perfect, right? So this portion here, m is equal to 1 minus n. When m plus 1 is equal to 1, I'm sorry, when m plus n is equal to 1. If this whole thing is 1, then m is equal to 1 minus n. And that's where we get 1 minus n. And this, if you recall from the last video, this is Euler's reflection. Okay, so this is exactly what we have. So now we can go ahead and apply it here. This is simply Euler's reflection. Right here, for sure, we want to know, okay, well, we know that this is going to be like n is like n 1 minus n, sorry. So if m is equal to 1 minus n, what is m minus 1? So m minus 1 is equal to negative 3/4, which means that m is equal to 1/4. So what we have is 1/4, 1 minus 1/4. Okay, just because there's nothing on this exponent here, we know immediately that this is Euler's reflection. Okay, so now we go ahead and apply Euler's reflection. So now this is equal the gamma of 1/4, gamma of 1 minus 1/4. Okay, then this means that we have pi cosecant of pi over 4. Okay, and this is simply equal to root 2 pi. Okay, very simple. We didn't have to do a power substitution and then partial fractions. We didn't have to do integration by parts. We didn't have to do any of that. We could just go straight into Euler's reflection. Okay, let's do another example. The integral that scares everyone. Tangent of x to the power of 1 over 2020. Or a rooted radical tangent of x. We're all traumatized by the square root of tangent of x, right? But now we can even have more power. So, of course, I mean, if you try to solve this indefinitely, then yeah, it's god awful. However, the from 0 to pi over 2 makes it so much simpler. Let me show you. If you let u equal tangent x, you should get from 0 to infinity, and you would end up like, well, we have u 1 over 2020, and then the substitution would give us like u squared plus 1 at the bottom, right? Okay, so how do we force an Euler's reflection formula on this? So what we do is we just turn this into a linear, or like to a 1 degree variable. So in other words, let w equal u squared. so that this would just be simply w plus 1. And so now we have from 0 to infinity, this would be w, let's see, half, so it'll be 1 over 40, w plus 1. And then we would also have like times 2 root w, so we would have like 2 minus 1 half. Okay, and so now we can, you can just start going into Euler's reflection here, right? Because we have w plus 1, there's nothing here. So that's where we know, okay, Euler reflection. So we just need to work on this. M minus 1 is equal to 1 over 40 minus a half. But with adding 1 to the other side, we get plus a half. So what we have is we're going to have 1 over 40 plus a half. And then we're going to have the minus 1 version, which is minus a half. Do you remember the other reflection formula from that previous video? It's the one with the secant, right? So this is equal to pi over 2, because of the half, pi over 2 secant of pi over 40. And that is our answer. Okay? So, yeah, that's pretty much it. Just kind of finding a way to put it in this form, that beta function form, and then, you know, utilize Euler's reflection. Okay? Alright, next integral. Whoa, now this looks a little much awkward, right? It's not a rational polynomial anymore. So what do we do with that cosine ln of x? Well, cosine of ln of x, that's a little suspicious. We can still turn it into, I wouldn't say a polynomial, but technically a polynomial. It's just that the exponent wouldn't be an integer, right? So what I'm saying is we can complexify this. We can actually complexify this. So this would be from 0 to infinity, x to the power of I plus x to the power of negative I over 2, and then leave this here. Okay, now trust me, let's see where this goes. Just trust me. So we have, if we split this, right, if you just kind of split this in two separate terms of integrals, okay, you would have like two different beta functions, right? So of course, well, let me just write it right here. We have a half, okay, and this first beta, we have what? So m plus n is equal to 2, right? But m is equal to I plus 1. So in that case, what we have here is n is equal to, if this is I plus 1, then we would have what? 1 minus I, right? So we have I plus 1 here, 1 minus I here. Okay, and this other portion here, right, plus, and then the other beta, right, you do the same thing, but this time it's m is equal to 1 minus I, then n for this n plus n. If 1 minus I is here, then we would have 1 plus I. Huh, interesting. So we technically kind of have the same thing in a way. So, okay. So let's do that. So this is technically 2 times, I think the half is going to cancel out. So now we have I plus 1, 1 minus I. Okay, I know I'm safe because the definition right, if I add the gamma here, if you add these two up, what do you get? Like gamma of 2, but gamma of 2 is equal to like 1, right? So I know that I would be safe to combine these two beta functions, right? If it was something else, then I wouldn't be able to combine it, depending on, as long as they have like the same gamma denominator, whatever. But this is what we have. Okay, so what do we do? So how do we solve this gamma expression here? Again, Euler's reflection, right? This is I plus 1, but we want I. We can definitely change this to I, right? Because this is I times gamma of I, right? And then 1 minus I here. And so by Euler's reflection, we have pi cosecant of pi I, right? And now, what is cosecant pi I? So let's write sine pi I. If you remember the definition of sine in complex terms, right, it was 2i e to the ix, which means pi I squared, which is negative pi, and then minus e to the negative ix, which is pi if we plug it in, right? And now this pi, this I here, 1 over I is negative I. I'm going to switch these two, so it becomes e to the pi minus e to the negative pi instead, so that negative cancels out. Okay, what does this look like? This looks like the definition of sinh. So this is I sinh pi. So what we have here is we actually have I times pi, then sine of pi I was I sinh of pi, and that imaginary number cancels out. How amazing is that? So this whole integral is equal to pi sinh pi over sinh pi. Okay, so that is our answer for this awkward looking integral. So again, beta function, if it doesn't turn, if it still has something here, still use beta function, and then kind of manipulate it here in a way where we use gamma or like the factorial property, and then use Euler's reflection to compute it. Okay? Alright, let's move on to another tricky integral. Alright, we have the fourth root of 1 over x minus 1. Interesting. How do we go about this? Right, so breathe, don't panic. I know this looks awkward. Let's start with small things, right? So, of course, this looks like 1 minus x over fourth root of x. Okay, what do we do here? So this looks awkward. This will definitely freak a lot of people out, because when you see it like this, it looks like a weird, awkward radical integral, right? This looks like something that would be nasty to do, trig substitution or something awful. Okay. However, people do miss that this can actually be easily solved using beta function. I think that's the thing, is like it's hard to see that this is this could be solved using beta function, right? As long as you have that 1 minus x, oh, beta function. It's just the radicals, the fourth root is just what's very distracting, and it doesn't, popped into your head. Oh wait, you could just use beta function. So this is simply beta function 1 minus x 1/4 and x to the power of negative 1/4 dx. Okay? And now this is simply a beta function, right? Let's see, well, how does the formula go? It was like from 0 to 1, 1 minus x m minus 1 x n minus 1 dx, right? So that means that our beta function would be m here. So 1/4 equals m minus 1. So m would be, what, 5/4? And then here, negative 1/4, it would be, so negative 1/4 equal to n minus 1. So n would be 3/4. Right? You could even switch it like n minus 1, m minus 1. You'll still come out with like the same beta function. It's gonna equal the same thing whichever you reroute it as. So don't you worry about that. Okay. So now this is simply what, 5/4 gamma 5/4 and gamma 3/4, and I know it's gonna be all over 1 because 5/4 plus 3/4 is gonna equal to 2. Gamma of 2 is equal to 1, so you just have 1 underneath, which just means this. So, okay, so we have this. Now what? How do we compute this? Again, 5/4, notice that 5/4 is bigger than 1, so that means we can use the factorial property, right? So, if you remember, x plus 1 is equal to x gamma of x. Okay, 5/4 is equal to 1/4 plus 1. So what this means is that this 5/4 part here is equal to 1/4 gamma of 1/4. And then that gamma of 3/4 is the same thing as 1 minus 1/4. Now it's easy for you to see that this is an Euler's reflection. So now we go ahead, this is 1/4, and using Euler's reflection, we have pi cosecant of pi over 4. Okay, and what does this equal? This is equal to pi root 2 over 4. Okay, and that is our answer for this integral. So this is a little tricky. This scares a lot of people, right? But if you see 1 minus x and then x here, whichever, if just in terms of 1 minus x to the power of whatever, x to the power of whatever, use beta function, right? It's a little, it could be, you can sometimes forget because these radicals are very distracting and it just makes you think, oh crap, this is like a weird, awkward trig substitution integral. But you can just simply solve it using beta function, okay? So don't forget about the beta function. Whoa, from 0 to infinity, we have the inverse cotangent of x to the power of 2023 over 2 dx. This looks crazy. Huh, what do we do? What do we do? So, let's try letting you, because I don't even know where to begin with this, right? We don't even know where to begin with this. So let's try let u equal x to the power of 2023. Let's try force u subbing it, just to see what happens. So we have 2023 over 2x and minus 1, which would be 2021 over 2 dx, right? Obviously, we don't have this portion, so we're going to do a force u substitution. Let u 2 over 2023 x, then dx is going to equal to 2 2023 u, minus 2023, so that's going to be a negative 2021 over 2023, right? Du. Alright, I know this looks daunting, but like, I mean, I think we could be fine. I think we'll just see where this leads to. Okay, so, see, 0 to infinity, we're gonna have 2 2023 u, or actually let me bring that u down because we have the exponent 2021 for 2023, and we have the inverse cotangent of u du. Okay, now why am I okay with this? The reason is because I'm planning to do integration by parts where inverse cotangent of u becomes 1 over like u squared plus 1, right? And I'm going to utilize that and kind of try to change that. I'm pretty much forcing it into a beta function. Okay, so inverse tangents or inverse cotangents are great ways to kind of apply integration by parts and then use beta function. So here, I'll go ahead and do that. So let me color this in green because this is, or actually I'll erase this first. We have inverse cotangent of u, and then we have like u to the power, let's just focus on, or actually, I'll bring the constant in so that I don't forget. And we have like u to the power of negative 2021 over 2023. Okay, this is going to become a positive 1 plus u squared, 1 over 1 plus u squared, because inverse cotangent, when you derive it, you get a negative out of it. Okay, and then here, we technically, I mean, this came from this, right? So u to the power of 20, it was, I'm sorry, it was, oh yeah, 2 over 2023, because we had to derive it from our u sub. Okay, if you plug in infinity, inverse cotangent of infinity is equal to 0. Okay, and then if you plug in 0, 0 goes here, and then this makes the whole thing 0 as well. So this means that this portion here is going to equal to 0. So what we have left is exactly from 0 to infinity, u to the power of 2 over 2023, all over 1 plus u squared du. And this is actually very nice. It's a very nice setup to perform beta function. So now we can go ahead and simply just let w equal u squared. Right? So we're setting up for a Euler reflection formula. So we have 2, 1 plus w, and this is now w. This is going to be like a half, so this, it would cancel out that 2, 2023, as well as the root w at the bottom that we had to force u sub with. Okay, and now, as you can see, this is simply beta, right? M minus 1, we get a half. Oh, we already know where this is going, right? You already know the other side is going to be like. And now, this is just, you know, Euler's reflection, but with the secant function. So now this is all over it. Don't forget the half, we nearly died. We have a half pi over 2 secant of pi over 2023. So our answer is pi over 2 times secant of pi over 2023. Okay, so a little tricky. It was a very scary process, right? The way we solved this integral, you know, when you see this, you definitely was not expecting to have a beta function come out of it, right? But inverse tangents or inverse cotangents, they are great ways to form it into this, and then get into the beta function form and solve using beta function and Euler's reflection. Okay. Okay, we have another scary integral here. Do not freak out. Don't freak out. Okay. Let's just kind of flip the negative. So we would have from 0 to 1 cube root of x minus x cubed. Right? Just starting the small things. We just want to start the small things, right? Unfortunately, this is not x times 1 minus x, because then we would just go straight into beta function. But unfortunately, we don't have that. So what do we do here? If we separate it, x1 minus x squared. Ah, okay. So notice that we could actually do something with this, right? It may not be x times 1 minus x, but we can definitely do a u substitution to kind of change that, right? Yes. So what we're going to do is we're going to go like this. We're going to have x to the power of negative 1/3, 1 minus x squared to the power of negative 1/3, right? And we can let u equal x squared. So now what we have, don't forget that this is a force substitution. So we have square root of u equal x. That means that for dx we have to do du over 2 root u. So you should definitely have this. Now it's a lot cleaner. Now we can actually go ahead and use beta function. Right, this is now the beta of 1/3 2/3 over 2. Right, this is definitely 1 minus 1/3. So obviously we can use Euler's reflection. So pi over 2, this would be cosecant of pi over 3. So our answer is what? Pi over 3. That's like root 3 over 2, 2 over root 3. Yeah, so our answer is cleanly pi over root 3. That is our answer. Okay, so scary radicals like this, you know, and then if you could try to separate it like this, try to use a beta function. Okay, because a lot of radicals scares a lot of people, and sometimes we tend to forget that it could be easily solved using beta function. Okay? Alright, so that was our last integral. I hope this was helpful. Again, go ahead and rewatch this video and try all the integrals yourself to kind of get comfortable with Euler's reflection. Okay? So I hope that was helpful. Thank you so much for watching, and I'll see you guys in the next part.